Hello and welcome. This is going to be our lecture video in which I'll be going over the Unit 1 review. Ideally, you've already completed this review, and this is just your chance to grade yourself and see the work for a couple of these problems. All right, so some true or false to get us started. Speed is distance divided by time. That is true. And I think a good way to remember this is just think of a typical unit for speed like miles per hour. Well, that's a distance divided by time. A unit for acceleration is meters per second. That is going to be false. Meters per second would be a unit of velocity, not acceleration. It would need to be meters per second squared. The brakes in your car accelerate your car. That one is true. Anything that changes velocity is called acceleration. Acceleration is just a change in velocity. Doesn't matter if it's speeding up or slowing down, both count as acceleration. A horizontal line on a distance versus time graph means an object is speeding up. This one is false. If it's distance versus time, a horizontal line would mean the object is standing still, not moving at all. The slope of a distance versus time graph is the speed. That is going to be true. The one thing is that we want to stop saying speed and start saying velocity, because slopes can be positive and negative, while speed is generally regarded as only positive. So if you wanted to argue that one being false because it should say velocity, I would accept it, but for all intents and purposes, this is a true statement. All right, what is the difference between speed and velocity? Let's see if I can type here. So we'd want to definitely answer this with full sentences. And it's what I basically just said. Velocity is speed plus direction. The speed is only a component of velocity. Velocity can be negative, while in general speed can only be positive. What are some possible units of speed? Let's think of some good ones. We already wrote that one, miles per hour. We'll write it again here. MPH, I think is fine. Another really popular one in physics is meters per second. But you can come up with lots as long as it's a distance unit divided by a time unit. You could have centimeters per hour. You could have yards per day. As long as it's a distance divided by time, it's a unit of speed. Feel free to come up with as many as you want there. When you look at the speedometer in your moving car, you see the cars. Well, it'd be easy to just say velocity here or maybe speed. I guess speed would actually be probably more appropriate because the speedometer is never going to give you a negative number, but we want to say instantaneous speed. Because often it's really important if we differentiate average speed versus instantaneous speed. The speedometer is always giving you your instantaneous speed. Acceleration is defined as the change in what over what. Hopefully you said velocity over time. Which of these does not involve acceleration? A car starts from rest at a traffic light and is going 30 miles per hour 5 seconds later, so that velocity did change, so that is acceleration. We have a dog that slows down, again, velocity changes, so that means that there is acceleration. Runs to a tree, stops, and runs back. So because the direction changed, and velocity is the speed and direction, we can say velocity changed in C as well. So it's got to be D. Let's make sure that makes sense. Bicycle traveling 10 meters per second covers 200 meters in 20 seconds. So constant velocity, there is no acceleration there. All right. A train travels 6 meters in the first second, another 6 meters in the second second of travel, and 6 meters again during the third second. Its acceleration is 0 meters per second squared. Even though it's going 6 meters per second at each instant, the acceleration is how much the velocity is changing by, and we can see this velocity does not change. Okay, we've got some matching here. Use the answers A to D. So blank speed at a specific moment in time. So what is speed at a specific moment in time? It's got to be C, instantaneous speed. Rate at which velocity is changing, that's going to be A, acceleration. The distance moved per unit time is just velocity. And then speed in a particular direction, that makes sense for our last remaining option, average speed. All right, moving down. So suppose you take a trip that covers 240 kilometers and takes 4 hours. What's your average speed? So when we're dealing with average speed, we don't really worry too much about acceleration. We're just going to use the formula distance equals speed times time. The trip covers 240 kilometers, so that's going to be our distance is 240. And it takes 4 hours, so S times 4. Now we'll solve for speed by dividing both sides by 4. And we get 60 equals S, and the unit here is kilometers per hour. So that would be moving pretty good for a car, but isn't quite highway speeds. All right, what is the distance a cheetah travels in 2.5 seconds if the cheetah stays running at a maximum speed of 30.6 meters per second? That's really moving. So again, we can use distance equals speed times time. So distance equals 30.6 for our speed, and then the time times 2.5. Seconds will cancel out, and we'll be left with the unit of meters. Let me plug this in. We get 30.6 times 2.5, 76.5 meters. So almost a full football field in 2.5 seconds. That's way faster than a human can go. All right, a student is running through the halls at CHS. As the student rounds the corner, he sees Principal Gacci and decelerates from 14 meters per second to 0 in 0.98 seconds. What's the student's acceleration? So here we can start to use some of our kinematic equations. This one, I'll use the formula final velocity equals initial velocity plus acceleration times time. And now let's fill in. Our final velocity is 0 meters per second, initial velocity 14, plus we don't know the acceleration, but we know it takes 0.98 seconds. Subtract 14 from both sides, we'll get negative 14 equals 0.98a. Divide both sides by 0.98. And we get negative 1.4 divided by 0.98 is negative 14.29. And then this is an acceleration, so be very careful with the units. It's going to be meters per second, or meters per second squared. So that's some pretty serious acceleration. That's about 1.5 g-forces to bring themselves to a stop so quickly. All right, a race car increases its speed from 45 meters per second to 85 meters per second in a period of 4.5 seconds. What's the acceleration of the car? Here I'm going to start, now we're getting even further into our kinematics. I'm going to start labeling things. So that's our initial velocity, that's our final velocity, that's our time, and we want to know the acceleration. So we want to pick the equation that doesn't even have distance in it. And again, it's the same equation as this one up here. So final velocity 85 equals initial velocity 45 plus the acceleration times the time of 4.5. Solve this, I'll subtract 45 from both sides. 40 equals 4.5a, divide both sides by 4.5. 40 divided by 4.5 is 8.9, we'll say 8.9 meters per second. So about a g-force. How long would it take a 700-pound gorilla to run 14 meters at a rate of 1.5 meters per second? So here we've got a distracting piece of information. It does not matter that it's a 700-pound gorilla. Does not matter. So don't be thrown off by extra information. For this one, you can just do distance equals speed times time. So it's going to run 14 meters. Its speed is 1.5 meters per second, and the time is still unknown. We divide both sides by 1.5. And we get 14 over 1.5, 9.3 seconds. All right, that's actually moving pretty slow, 1.5 meters per second. So this gorilla, it's not really running. It's more of a jog maybe. Number 6, a student drops a pebble from the edge of a vertical cliff. The pebble hits the ground after 4 seconds. So let's label that as our time. After it was dropped, what is the height of the cliff? So it feels like we don't have enough information here because we only have the one piece. We know we need to have 3 pieces, but we can infer a couple others. If it's dropped, its initial velocity is probably 0. And as long as this cliff is on Earth, we can say the acceleration is 9.8 meters per second. So with this, now we do have 3 pieces of information, and we can figure out the height of the cliff, or d. The only thing we are missing is final velocity, and we don't care about final velocity, so we'll pick the equation that is d equals initial velocity times time plus 1/2 at squared, and then fill in all of the information. So we don't know distance, but we know if initial velocity is 0, time is 4 seconds, 1/2 times 9.8 times 4 squared. I'm going to plug all of that into my calculator. Notice that this term goes away. So 0.5 times 9.8 times, I'll just do 16 because I can do 4 squared in my head. And I get that my distance equals 78.4 meters. Our acceleration was in meters per second, so the distance is going to be in meters. Next up, an airplane accelerates down a runway at 3.2 meters per second squared for 32.8 seconds until it finally lifts off the ground. So let's see, we've got acceleration, we have time. We can assume the initial velocity is 0 again. Determine the distance traveled before takeoff. So it looks like we have a pretty similar setup as last time. Distance equals initial velocity times time plus 1/2 at squared. This term will go away again because initial velocity is 0, so distance equals 1/2 times 3.2 times 32.8 squared. 0.5 times 3.2 times 32.8 squared. I get 1,721.34 meters. Next up, the car starts from rest and accelerates uniformly. So again, starts from rest. Again, we can say initial velocity is equal to 0. We have a time, we have a distance, and we're going to try to figure out the acceleration. So we don't care about final velocity. So again, we'll use that same formula, but we're solving for a different part of it. So distance is 110 meters. Initial velocity is 0. So that first term goes away. And we have 1/2 times the acceleration times 5.21 squared. Let's just plug in the 1/2 times 5.21 squared. So we can get all of that is 13.57. So 110 equals 13.57a. Divide both sides by 13.57. And we get a equals 110 divided by second answer. I get 8.1. And now it's an acceleration. Everything was in meters and in seconds. So this is meters per second per second. All right, next up, we got Mr. Bowman, who's riding the giant drop at Great America. It's an amusement park ride. He free falls for 2.6 seconds. What will be his final velocity? So we can assume initial velocity of 0 again. Final velocity is the question mark. Time is 2.6, and our acceleration is 9.8. And I'm just designating down as the positive direction. So I don't have information about distance, and I don't care about distance. So final velocity equals initial velocity plus AT. So final velocity equals 0 plus 2.6 times 9.8. Final velocity equals 2.6 times 9.8, 25.48 meters per second. It's a velocity, so just meters per second is fine. All right, a feather is dropped on the moon from a height, so our distance equals 1.4 of 1.4 meters. The acceleration of gravity on the moon is 1.67 meters per second squared. If it's dropped, again, we can assume the initial velocity is 0, and we're just trying to figure out the time here. So I'm going to use distance equals initial velocity times time plus 1/2 AT squared. All right, 1.4 meters. This term will go away again, times 1/2 times acceleration 1.67 times t squared. And we just solve from here. Half of 1.67, 0.835 times t squared. I divide both sides by 0.835. 1.4 divided by the second answer. I get 1.67. We've got to round up to 8 equals t squared. I'm just going to keep it in my calculator and take the square root. So second square root of second answer. I get 1.29 seconds. So yeah, things definitely fall slower on the moon. And on to some graphing. We've got a student that's running in the halls of CHS, being chased by Mr. Mossman. A conceptual physics student collects the following data about the running student, calculate the velocity of each interval, draw a distance versus time graph on the graph paper, and calculate the slope, then create a velocity versus time graph. All right, so one thing that's kind of a tricky part about velocity is that it's not total distance divided by time. It's the individual intervals divided by how long that interval took. So this one, the change in distance was 3.2 meters, and it took 1 second, so 3.2. Here, the change is 3.3, and it took another just 1 second, so 3.3 divided by 1 is 3.3 meters per second. And then it looks like it went up by another 3.3 in another 1 second. And then it goes up by a 3.2. And then a 3.1, which gives us 3.1 meters per second. So let's see if we can create a distance versus time. We're just going to focus on the two columns on the left. So this one and this one. Let's pick a scale that makes sense. This looks to be about 10 boxes tall, and I want to be able to fit data in all the way up to 16.1 meters, so maybe I'll count by twos. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. All right, and that's meters for our distance. And then time always goes on the x-axis. So this is time, and I think seconds is the unit, and I think we can maybe count by even 2 boxes. This is every second to really spread this out. 1, 2, 3, 4, 5, 6, and that's more than enough. So at 0 seconds, they've traveled 0 meters, so put a point right there. Then after 1 second, it's 3.2, so 1, 3.2 would be right about there. Then after 2, 6.5. 3, they're at 9.8. Then 13, and then 16.1. And it is fair to connect these up, since we had to pass through all those intermediate points to reach these spots. And now we'll create a velocity versus time. All of our velocities are very close to 3. So it looks like I got moved on to my next sheet. All right, so again, time goes on the x-axis, measured in seconds. And then this is going to be velocity as measured by meters per second. And we can count by twos here, maybe 0, 1, 2, 3. Same thing over here, 0, 1, 2, 3, 4, 5. And all of our data points are right around 3. So we're going to see pretty much a horizontal line here, which shows constant speed. I don't have the exact numbers right in front of me because I had to switch pages, but the graph's going to look a little bit like that. So they run with a constant speed. All right, that's that for this lecture video. No embedded questions, just making it to the end of the video is going to be good enough for this one. And have a good rest of your day.